Hello guys, welcome to another video. Today we're going to practice topic 1, a couple of multiple choice questions. So let's jump straight to it and see the solutions. So for the question 1, it asks which quantity has the fundamental SI units of kilograms over meters per second square. So here you can just try to figure it out which quantities are they, but it's gonna take you a long time. So I think a faster solution here is to check each one of those, what kind of fundamental units they have. So let's talk, for example, about energy. Let's take potential energy, MgH. The units are kilograms times meters per second square times meters. So nothing similar to that. So energy is not. Forces will have mass times acceleration, so it's kilograms times meters per second square. Not even close to that. Momentum, it's mass times velocity, so it's kilograms times meters per second. Neither this one. So probably it's gonna be number D, because nothing else it is, but let's look at it. Pressure, it's force over area. Now force is kilograms times meters per second square. Area, it's meters square. So if you simplify this fraction, you have kilograms over meters times second square. And this is exactly what we are looking for. So the correct answer is D. Now in number 2, it says that we have an object that is held in equilibrium, it's important, by three forces of magnitude F, G, and H that act at point at the same plane. So here we see the shape and we understand very straight away that this needs to be in equilibrium. So the Fx component of F, it needs to be equal with G, and the Fy component of F, it needs to be equal with H. So it says like three equations for these forces are the following ones. Which equations are correct? Now we need to check each one of those and see what is correct and what is not. The first one, of course, it's correct. I said the component of the x, the adjacent of the f, the adjacent, it needs to be equal with g, so it's definitely correct. The last one, it says that the force F is equal with g and h. Of course, this cannot be true. Now what about number 2? So here is the tricky part. You have to create this equation in order to see if it's true or not. So let's start about creating this second part of the equation. What is the g cosine theta plus h sine theta? So I'm going to start with the cosine first. Cosine theta is the fx over f, adjacent over hypotenuse. Now as I said before, this is g, the fx is g over f. So what I want to do, I want to have g times cos theta. So I'm going to multiply both sides by g, and what I get is that g cosine theta is equal with g squared over f. I will do the same for the sine theta. Sine theta is equal with the opposite over the hypotenuse. So from here, the opposite is the fy, so it's actually the h over f. So I'm going to multiply both sides by h. So I have the h sine theta is equal with h squared over f. So I'm going to add those two now in order to get this relationship. So g cos theta plus h sine theta is equal with g squared plus h squared over f. Now you know also from Pythagoras theorem that the f squared is equal with fx squared plus fy squared. So that means that f squared is equal with g squared plus h squared. So if you replace this relationship here, you have f squared over f. These are cancelled out, so this is equal with f. So also this equation, it is true. This is a tricky one. It takes a little bit of time, but with a lot of practice you will be able to do that fast. Now number 3, it says what are the units of specific energy and energy density? Now we need to remember these two formulas for specific energy and energy density. Specific energy is the energy over the mass. And energy density is the energy over the volume. Now, these two equations, they are not in your data booklet. As I said before in the previous video when I was explaining the data booklet, I said that there are a couple of equations that they are missing. So what we need to do is to place them down in our own data booklet. So after a lot of practice, you're going to memorize those equations. So in problems like this, it's gonna be quite easy and fast for us to solve it. So what I have energy over mass. So it's kilograms over, joules again over kilograms. So either B either C. And then I have energy over volume. So it's joules over meters cubed. So of course from here the only correct answer is B. So number 6. It says that the student wants to determine the angular speed omega of a rotating object. The period t is 0.5 plus minus 5%. The angular speed omega is given by this formula. What is the percentage of certainty of omega? So here we know the percentage of certainty of t. We don't have any other variables in this equation. This is a constant, so we don't care about any uncertainties. So omega, it has to have the same uncertainty. So the answer is C. Now number 7. It says that the student models the relationship between the pressure P of a gas and its temperature T as this equation. The units of P are Pascal and the units of T are Kelvin. What are the fundamental units of X and Y? So first of all, we know that Pascals are not the fundamental units for pressure. The fundamental units for pressure, they get found, as we saw before, from the force over the area, and it's kilograms over meters per second square. So meters to the power of -1, seconds to the power of -1. So having this relationship now, x plus y times t, you know that these both terms, they need to give you the same units of whatever you have here. So these ones are these fundamental units. So definitely x, it has to have the same. So the x, it has to have the same units as this one. And of course here, it can be either A, either B. Now what is happening in the second term? In the second term, you need to have the same units. You need to have kilograms, meters to the power of -1, sorry, this is 2, times seconds to the power of -2. But also you multiply temperature here. So you need also to include the units that they will cancel out the units of temperature. And these are Kelvin, so you need to divide by Kelvin, so it's time kelvins to the power of -1. And this, of course, are these two options, and your answer is A. Number 8. Number 8, you have a student that measures the radius r of a circular plate to determine its area. The absolute uncertainty in r is delta r. What is the fractional uncertainty in the area of the plate? Fractional uncertainty. First of all, we need to remember that the fractional uncertainty is given by the absolute uncertainty over the value of the measurement. So the area, it will be given on a circular plate, if you know the radius, by the pi times r squared. So what we have here, we have r squared, that means that r multiplies itself, and of course, in order to take this uncertainty, the fractional uncertainty in the area, it's gonna be the fractional uncertainty of the radius, but multiplied by the exponent. The exponent is to the power of 2, so you have to multiply this number by 2. So this is the number A. In your data booklet, you can find this formula. You can easily see it from there. You can solve this question very easy. Number 9, it asks what is the unit of electrical potential difference expressed in fundamental SI units. So again, we have something similar. We need to find the units of potential difference. Potential difference is given by the work done over the charge. Now we need to find the fundamental units for work done. Work done is force times distance. So kilograms times meters per second square times meters times distance. So this, it will be kilograms times meters per second square times seconds to the power of -2. And for the Q for the charge, the units are coulombs, but these are not the fundamental units. We need to express the charge from fundamental units based quantities. So what do we know? We know that the current is the rate of the charge that it flows. So from here I can solve for Q, that is the current times the time, and fundamental units, both of them they are fundamental quantities, so they have units of amperes times seconds. So if I try to solve for the potential difference, I have kilograms times meters squared times seconds to the power of -2 divided by amperes times seconds. So these ones they go up, so you have kilograms times meters squared times seconds to the power of -3 times amperes to the power of -1. And this, of course, is the number C. The number 10 is that an object has a weight of 6.10 times 10 to the power of 2 newtons. What is the change in gravitational potential energy of the object when it moves through 8.0 meters vertical? So here what you can do, you can just start solving this equation, but this is not important because we don't care about the solution of this problem, we care about the significant figures here. And as you see, both quantities, they have the same number of significant figures. There are 2. So you're looking at an answer of 2 significant figures. So it's just B. You don't have to calculate anything here. Because if you calculate, you're going to find that the correct answer is C. You're going to find the number 8 times 6.10. It's going to give you 4.88. But of course, these are not the case here. We want 2 significant figures in our answer. And number 11, we have a student that is verifying the equation x is equal to 2 times lambda times y over z. The percentage uncertainties are here 10% for lambda, 0.05% for y, 5% for z. What is the percentage uncertainty in x? So in order to find the percentage uncertainty, as already we have them, we need to add the individual uncertainties of each variable. Now, of course, here there are multiplications and divisions, so we just add the percentage uncertainties. So we have lambda 10% plus y 0.05% plus z 5%. So this it will give you an answer of 15.05%. Of course, this is insignificant for us. Here you don't have any other answer close to it apart the B. So that was it for today, guys. Topic 1, it's an easy topic. You need to study and practice in order to be familiar with everything. So study hard and good luck.